Every single star you can see is just a tiny sliver of what is actually there. We live inside a bubble called the Observable Universe, a sphere of everything whose light has had time to reach us. But this cosmic horizon is not the end. It is merely the limit of our vision, a frontier hiding profound secrets. By the end of this journey, you will understand the mind-bending theories scientists have for what lies beyond our cosmic horizon. We will explore if our universe is just one of countless others in a vast multiverse, and if the very edge of reality could be a two-dimensional projection. What do you believe could be waiting in the infinite dark beyond our sight? This cosmic bubble we inhabit is almost unimaginably vast. Picture every galaxy, every star, and every planet you have ever seen in a telescope, all contained within a sphere roughly 93 billion light-years across. This is our observable universe, and we are at its center, but this is not a position of privilege. It is simply a consequence of light's finite speed. Every point in the cosmos has its own observable universe, its own unique sphere of visibility. The true nature of this horizon is not one of walls or edges, but of time. It marks the boundary beyond which light emitted at the moment of the Big Bang, nearly 13.8 billion years ago, has not yet had enough time to reach our telescopes. It is our past cosmic horizon, a limit set by the very age of the universe itself. This creates a profound illusion. We look out into space and see galaxies racing away from us, as if we are the center from which everything is fleeing. The reality is far stranger. The space between galaxies is itself stretching, carrying them apart like raisins in an expanding loaf of bread. This expansion is the key to understanding our cosmic prison. It means that for galaxies beyond a certain distance, the space between us is growing so fast that their light can never bridge the gap. They are forever receding over our event horizon, vanishing from our future view. So the edge of our bubble is not a physical end to reality. It is simply the final frontier from which any information can ever reach us. The universe beyond that horizon could be infinite, but we are forever isolated from it, trapped inside our ever-shrinking island of visibility. This expansion creates a permanent curtain drawn across the cosmos. Because space itself is stretching, the most distant galaxies are racing away from us at velocities that actually exceed the speed of light. This is not a violation of Einstein's laws, because nothing is moving through space faster than light. The space between objects is simply growing. The result is a fundamental and unbreakable limit, a particle horizon. Picture a ship sailing toward you on a current that flows faster than the ship can possibly sail. No matter how powerful its engine, it will never reach you. It is forever carried backward by the tide. This is the fate of light from the farthest reaches. We see the ancient glow of galaxies near this horizon, a snapshot from billions of years ago, but we can never see what they have become. Their present and everything that lies behind them is lost to us forever. This horizon is not a fixed wall in space. It is a moving boundary in time that will always conceal a portion of the cosmos as the universe ages. It is a one-way street into the past. We are archaeologists of the cosmos, sifting through ancient light, but the universe as it exists right now, in its entirety, remains fundamentally unknowable. This is the core of our cosmic isolation. If information cannot cross this barrier, how can we ever claim to know what lies in the infinite dark beyond? That ancient light, the echo of creation we call the cosmic microwave background, is our ultimate time capsule. To truly grasp the nature of our cosmic horizon, we must rewind the clock all the way back to the very beginning. The Big Bang was not a conventional explosion flinging debris into a void. It was the sudden, violent expansion of space itself, everywhere at once. In its earliest moments, the entire universe was compressed into an unimaginably hot, dense state, a searing soup of fundamental particles. For nearly 400,000 years, the cosmos remained a thick, opaque fog. Light particles, photons, were constantly scattered and absorbed, trapped in a swirling plasma, unable to travel any meaningful distance. Then, in a pivotal moment, the universe cooled just enough for atoms to form. This event, known as recombination, suddenly cleared the cosmic fog. For the first time, light was set free, streaming across the universe in every direction. That first burst of liberated light is what we detect today as the cosmic microwave background. It is a baby picture of the cosmos, a snapshot from a time long before the first stars were born. This faint, cold glow fills the entire sky, and it marks the absolute limit of our direct vision. The edge of our observable universe is not a physical barrier in space. It is this primordial wall of light, a fossilized moment from when the universe was just an infant. Yet this is only the opening chapter. The universe continued its dramatic expansion, evolving structures and realms that this initial glow could never reveal. So when we peer at the CBM, we are not just looking at the edge, we are looking at the foundation upon which everything we know was built. This foundational event raises an even deeper question. If the CBM is our oldest view, what does the geometry of this infant universe tell us about the shape and ultimate fate of everything that lies beyond our sight? This foundational snapshot, the cosmic microwave background, does more than just show us the universe's infancy. It holds the key to its overall shape. The geometry of our cosmos is not a simple abstract concept. It dictates whether the universe is truly infinite or if it possesses a finite, yet unbounded form. Scientists have probed this geometry by meticulously studying the subtle patterns in the CMB's glow, looking for tiny temperature variations that act as cosmic fingerprints. They have mapped the vast web of galaxies, measuring how space itself behaves on the grandest scales. The collective evidence points overwhelmingly to one conclusion. Our universe appears to be geometrically flat. In a flat universe, the classic rules of geometry you learned in school hold true. Parallel lines will never meet or diverge. The angles of a triangle always add up to 180 degrees. This flatness is deeply significant because it is consistent with a universe that is infinite in extent. Imagine an endless, perfectly flat plane stretching forever in all directions. Now consider the alternatives. The universe could have been closed, shaped like the four-dimensional analog of a sphere. In this finite cosmos, if you traveled in a perfectly straight line, you would eventually loop back to your starting point, never encountering an edge, much like an astronaut circumnavigating the globe. Or it could have been open, curving outward like a saddle, also stretching into infinity but with a dramatically different set of rules. The data, however, keeps bringing us back to flat. This presents a profound conceptual challenge. If the universe is flat and infinite, then the observable cosmos is not just a bubble within a larger, hidden whole. It is an infinitesimally small patch of an endless reality. The very idea of an edge becomes meaningless. There is no beyond to travel to because everything that exists is already here, stretching forever. So what then is our cosmic horizon? It is not a boundary to something else. It is merely the limit of our vision within an endless expanse, a temporary window into a cosmos so vast that most of it is forever rushing away from us, lost to the relentless expansion of space. This flat, seemingly infinite cosmos we observe is the direct result of a violent and spectacular birth. The universe we see is so uniform, its geometry so perfectly balanced that it points to a singular, dramatic event in its first fleeting moments. A fraction of a second after the Big Bang, something extraordinary happened. The infant universe was seized by a force that caused it to expand at an unimaginable speed, far exceeding the velocity of light. This is the theory of cosmic inflation, a period when the very fabric of reality stretched exponentially, smoothing out any wrinkles and setting the stage for everything to come. Think of blowing up a balloon that has a few small wrinkles on its surface. As you inflate it, those wrinkles are stretched so thin they become virtually invisible. The entire surface becomes smooth and flat. This is what inflation did to our cosmos. It took a tiny, chaotic patch of the primordial universe and stretched it to an enormous size, creating the vast, uniform expanse we observe today. This explains why the cosmic microwave background looks almost the same in every direction, and it perfectly accounts for the flat geometry we measure. The universe appears flat because our entire observable cosmos is just a tiny, smoothed-out fragment of that initial, explosive growth. But this leads to a truly staggering possibility. If our entire observable universe, all 93 billion light-years of it, inflated from one microscopic region, what happened to the rest of the primordial cosmos? The theory suggests that inflation did not happen just once in one place. It could be an eternal process, happening in different patches of a greater meta-reality. While our local region stopped inflating and evolved into the universe we know, other regions completely disconnected from our own could have undergone their own inflationary bursts. Each of these patches would have blown up into its own separate, self-contained universe with its own unique properties, its own laws of physics, and its own cosmic horizon. What we call the entire universe may be nothing more than a single bubble in a frothing sea of infinity, a lone island in an infinite cosmic archipelago known as the multiverse. The edge of our observable cosmos, then, is not the edge of reality. It is merely the boundary of our local inflationary bubble, the limit of our vision within one pocket of a reality so vast it defies comprehension. Our search for the edge suddenly transforms. We are no longer just asking what lies beyond our horizon. We are asking if our entire reality is just one of countless others, each forever hidden from view. This transforms our cosmic horizon from a simple limit of sight into a border between realities. The Multiverse Hypothesis suggests that our entire universe, with all its galaxies and laws of physics, is just one bubble in a frothing, infinite cosmic sea. Each of these bubbles is a self-contained universe born from its own burst of eternal inflation. They are not far away in our space, but exist in a higher dimensional expanse, a meta-reality we call the bulk. Imagine a vast, calm ocean where bubbles are constantly forming, growing, and drifting apart. Each bubble contains its own unique atmosphere, its own rules of chemistry and physics. Our home is just one of these bubbles. We are forever trapped inside its film, unable to perceive the ocean outside or communicate with the other bubbles floating in the dark. The edge of our observable universe is not a place you could travel to. It is the point where our local physics and reality simply end, giving way to the foreign, higher dimensional bulk. No light, no information, no force from our universe can cross that divide. This is the ultimate cosmic isolation, a separation not of distance but of fundamental existence. Some theories, like string theory, propose an even more dizzying prospect, a vast landscape of possible universes. In this view, the fundamental constants of nature, like the strength of gravity or the mass of an electron, could be different in each bubble. In one universe, gravity might be so weak that stars never form. In another, the nuclear forces might be too strong, locking all matter into inert lumps. We happen to live in a bubble where the constants are just right for atoms, planets, and life to emerge. This is the Anthropic Principle in its grandest form, a cosmic lottery where we simply drew the winning ticket for a habitable reality. So the question shifts profoundly. It is no longer just what lies beyond our horizon in space, but what kinds of reality are possible beyond our physics. Are there universes made of pure light, or realms where time flows backward? The edge of everything we know may be the shoreline of an infinite ocean of creation, a frontier we can only explore with the power of thought. This holographic view of reality turns our deepest intuitions inside out. We perceive a world of 3 dimensions of height, width, and depth, a universe filled with solid objects and vast, empty spaces. Yet, the holographic principle proposes a stunning possibility. All of this, every galaxy, every star, every person, and every thought, might be nothing more than a magnificent illusion, a projection from a flat, 2-dimensional surface at the very edge of our cosmic horizon. The information required to describe every particle within our entire observable universe could be perfectly encoded on its outer boundary, like a cosmic DVD storing a 3-dimensional movie. This is not science fiction. The idea has its roots in one of the most mysterious objects in nature, the black hole. When matter falls into a black hole, it vanishes behind an event horizon, a point of no return. For decades, physicists were haunted by a paradox. According to quantum mechanics, information can never be truly destroyed. But if nothing can escape a black hole, what happens to the information describing the star that collapsed to form it, or the hapless astronaut who fell inside? The resolution came from an unexpected place. The information is not lost. It is not crushed into the central singularity. Instead, it is meticulously stored or painted onto the 2-dimensional surface of the event horizon itself. The black hole's boundary becomes a perfect hard drive, encoding everything within its volume. Now, take this radical idea and apply it to the largest boundary we know, the cosmic horizon of our entire observable universe. Could our reality also be a holographic projection? Is the edge of everything we can see actually a shimmering, 2-dimensional screen containing the complete blueprint for our 3-dimensional world? This would mean that the true fundamental reality is not the spacious volume we inhabit, but the information-rich surface at its limit. The desk you are sitting at, the device you are watching this on, the very thoughts in your mind would be incredibly detailed and complex holograms emerging from that distant, flat surface. The edge is not a place you could ever visit. It is the source code of existence. This blurs the line between the universe and its boundary until they become one and the same. We are not looking out toward a horizon. We are living inside a projection cast from that horizon. So if the universe is a hologram, what kind of projector could possibly be powerful enough to create such a consistent and tangible illusion? And what does that imply about the ultimate nature of the reality that hosts it? The very fabric of our cosmic isolation is being woven tighter by a mysterious force. In the late 1990s, astronomers made a discovery that overturned our most fundamental expectations about the cosmos. By observing distant supernova, they found that the universe's expansion is not slowing down due to gravity, as everyone had assumed. It is accelerating. The cosmos is flying apart at an ever-increasing rate, driven by something we cannot see, a phenomenon we call dark energy. This is not a gentle nudge. It is a powerful, repulsive force woven into the fabric of space itself, and it is now the dominant actor in the cosmic drama. As dark energy pushes galaxies apart, it actively forges our horizon. Each galaxy that crosses this threshold is not just drifting away, it is being forcefully ejected from our future by this relentless pressure. The edge of our observable universe is not a passive boundary, it is a receding wall of darkness, and dark energy is the engine pulling it closed around us. This acceleration paints a startlingly lonely future. Billions of years from now, the expansion will have carried all other galaxy clusters beyond our cosmic horizon. The light from those distant islands will have stretched beyond detectability, their signals forever lost. The night sky for any future astronomers in our local group will be profoundly empty. They will see only a handful of nearby galaxies, all bound together by gravity, drifting in an immense and impenetrable blackness. The entire vast cosmic history we now observe, the evidence of the Big Bang and the expanding universe, will have vanished from their view. The universe will appear static, small, and island-like. The edge will have shrunk to the borders of our own galactic neighborhood. This means that the window for cosmic discovery is not permanently open. We live in a privileged era, a golden age of cosmology where we can still see the evidence of the larger cosmos and deduce its origins. That window is slowly closing. So the mystery of dark energy is not just an academic puzzle. It is the key to understanding the ultimate fate of our cosmic perspective. What is this force that commands the final form of our reality? Is it a constant property of empty space or a dynamic field that could change again? The answers will determine whether the edge of everything becomes a permanent, silent tomb, or if some even stranger destiny awaits the cosmos. Dark energy holds the key to the universe's final act, a conclusion written in the geometry of empty space itself. The ultimate fate of our cosmos hinges on the precise character of this mysterious force. One possible destiny is known as the heat death. In this scenario, dark energy remains constant, and the acceleration of the universe continues at its current, steady pace. Billions of years from now, the last stars will flicker out, their fuel exhausted. Galaxies will drift ever farther apart, their lights vanishing over our cosmic horizon until our entire observable universe contains only the corpses of stars, black holes, and cold, lonely planets. Over trillions upon trillions of years, even these remnants will decay. Black holes will slowly evaporate through a quantum process, and all matter may ultimately decay into radiation. The universe will approach a state of maximum entropy, a final, uniform sea of incredibly dilute particles and energy, where the temperature everywhere drops to just a whisper above absolute zero. In this frozen, eternal twilight, the cosmic horizon still exists, but the universe within it is a vast, dark, and lifeless cemetery. There are no more events, no more changes. Time itself loses all meaning, but there is another, far more violent possibility, a finale called the Big Rip. This occurs if dark energy is not constant, but instead grows stronger over time. In this terrifying scenario, the repulsive force would eventually overcome every binding force in the universe. First, the acceleration would tear apart galaxy clusters, then individual galaxies. As the force intensifies, it would rip stars from their galactic homes. Closer to the end, the fabric of space-time would stretch so violently that it would pull planets from their stars. In the final moments, the force would overcome the gravity and electromagnetic forces holding objects together. Mountains would be torn from planets, and planets themselves would be shredded. Then it would reach down to the atomic scale, ripping molecules, then atoms, and finally nuclei and subatomic particles apart. In this cataclysm, the very fabric of space-time is torn asunder. The cosmic horizon, the limit of our observable universe, would be destroyed along with everything else. There is no more boundary because there is no coherent space-time left to define one. The edge of the universe, in this case, is not a location but an event, a final, singular moment when the structure of reality itself is unraveled. These two endpoints represent the final, temporal edge of everything. They are the absolute limits of cosmic history, the ultimate exploration of time and structure. The nature of the edge we ponder today is therefore inseparable from this final destiny. Is our universe destined for a long, cold sigh or a final, catastrophic scream? The answer is written in the invisible push of dark energy, a force that will one day dictate the last page of our cosmic story, and with it, the ultimate meaning of the edge. These grand cosmic structures were born from the tiniest of whispers. The entire cosmic web, with its galaxies and vast voids, can be traced back to microscopic ripples in the fabric of reality itself. In the searing energy of the universe's first moments, empty space was not truly empty. It was a turbulent sea of quantum fluctuations, where particles and energy flickered in and out of existence, a fundamental uncertainty woven into the nature of things. These fleeting disturbances were the primordial seeds of everything. Then came the brief, violent period of inflation. This exponential stretching acted like a cosmic magnifying glass, taking those infinitesimal quantum ripples and expanding them to astronomical proportions. The tiny hills and valleys in the primordial energy field were frozen into the fabric of space, creating regions that were ever so slightly denser than others. Over billions of years, gravity did the rest, pulling matter toward these dense spots. The hills grew into galaxy clusters, and the valleys stretched into the great cosmic voids we observe today. This direct lineage is permanently etched into the sky. The subtle patterns you see in maps of the cosmic microwave background, the hot and cold spots, are not random. They are the fossilized imprint of those initial quantum fluctuations, a baby picture of the universe's original texture. When we peer at the edge of our observable universe, we are not just looking at ancient light. We are witnessing quantum mechanics written across the cosmos, the rules of the infinitesimal scaled up to a cosmic panorama. The very laws that govern the behavior of atoms and photons are also the architects of the galactic superclusters. This forces a profound realization. To truly comprehend the edge of everything, we must look not only outward with our telescopes, but inward to the quantum foundation of reality. The boundary of our cosmos is not just a physical limit, but a testament to a deep, underlying unity, where the smallest and the largest scales of existence are inextricably linked. This faint microwave glow is the oldest light in existence, a direct messenger from the edge of time. It fills the entire sky, a cold whisper from a time when the universe was a mere infant, just 380,000 years old. This cosmic microwave background is not just a relic. It is our most detailed map of the cosmic horizon itself. The subtle temperature variations in this glow, tiny fluctuations of just 1 part in 100,000, are not random noise. They are the blueprint for the entire cosmic structure we see today. By meticulously mapping these patterns, scientists can read the universe's vital signs. They can measure its age with astonishing precision, calculate its total density, and confirm its flat geometry. They can even determine that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos, with the rest being the mysterious dark matter and dark energy. The CBM is the ultimate cosmic fossil, and its imprints tell us exactly how our local bubble of reality was forged. This primordial shell of light marks the absolute limit of our direct vision. When we look at it, we are not looking at an object in space. We are looking at a surface in time, a spherical wall that surrounds us at a distance of 13.8 billion light-years. Every direction we point our telescopes, we eventually hit this wall of ancient plasma. It is the final photograph from the universe's earliest childhood, a snapshot taken just after the fog cleared. But this photograph is also a powerful tool for peering beyond our own horizon. The specific patterns of hot and cold spots encoded in the CBM are a direct prediction of cosmic inflation. They are the magnified fingerprints of those initial quantum fluctuations stretched across the entire sky. The statistical properties of these patterns match what we would expect if our entire universe was born from a brief, explosive period of inflationary growth. This gives us our strongest indirect evidence for the multiverse. If inflation happened here, and if it is eternal, then our universe is likely just one bubble among countless others. The CBM cannot show us those other bubbles directly, but its detailed structure strongly suggests that our cosmic horizon is not the edge of reality, only the edge of our particular island in a vast, frothing metacosmos. This ancient light is therefore a two-way mirror. It shows us our own deepest past while simultaneously hinting at a reality beyond our own, a hidden multiverse whose existence we can only infer from the echoes within our own. But we are not limited to light alone in our quest to see beyond the horizon. There is another, far more penetrating messenger traveling through the cosmos, one that could carry a pristine record from the very birth of space and time: gravitational waves. These are not waves of light or sound, but literal ripples in the fabric of space-time itself, generated by the most violent cosmic events. When massive objects like black holes collide, they send shudders through the cosmic medium, stretching and squeezing the distances between everything. Yet the most sought-after signals are not from recent cataclysms, but from the universe's first fleeting instants. During the period of cosmic inflation, when reality expanded faster than light, the quantum foam of the infant universe would have been violently shaken. This turmoil would have spawned a background sea of primordial gravitational waves, a fossil imprint of inflation's incredible energy. Why are these waves so special? Light, our traditional cosmic messenger, was trapped and scattered in the hot, dense plasma of the early universe for hundreds of thousands of years. Gravitational waves, however, interact with matter so weakly that they can travel almost completely unimpeded. They would have streamed freely through that opaque primordial fog, carrying a clean, unaltered snapshot from a time long before the cosmic microwave background was created. Detecting this primordial hum would be like switching from a blurry, ancient photograph to a high-fidelity audio recording of the Big Bang's first moments. It would provide direct, smoking gun evidence for inflation, confirming that our universe underwent that fantastic growth spurt. The character of these waves, their specific frequency and amplitude, would tell us about the incredible energy scales at which inflation occurred. This, in turn, could offer profound hints about the fundamental physics that governs not just our universe, but the entire multiverse, revealing the engine that drives eternal cosmic creation. We are on the cusp of opening this new sensory channel to the cosmos. Observatories like the space-based LISA mission are being designed to listen for these faint whispers from the dawn of time. This emerging field of multi-messenger cosmology, combining the old light with the new vibrations, promises to revolutionize our understanding. We may soon not just see the edge of our observable universe, but truly hear the echoes of what lies beyond it. An infinite cosmos presents a paradox that challenges the very foundation of prediction. If our universe stretches on forever, or if it is just one member of an infinite multiverse, then every event that is physically possible must occur. Not just once, but an infinite number of times, somewhere in a galaxy far beyond our horizon, an exact copy of you is listening to this same sentence. Another version of Earth has already been destroyed by an asteroid, and another has yet to be formed. In a reality without boundaries, the improbable becomes inevitable. This is the heart of the measure problem in cosmology. How do we assign probabilities? How do we decide what is likely or unlikely when everything happens an infinite number of times? The concept of typicality breaks down completely. If there are an infinite number of universes where the laws of physics are just right for life, and also an infinite number where they are not, which infinity is larger? Both are endless. Comparing them is like asking if there are more even numbers than whole numbers. Both sets go on forever. This is not just a philosophical curiosity. It strikes at our ability to do science. For theories like eternal inflation and the multiverse to be scientifically valid, they must make testable predictions. But if every possible outcome is realized somewhere, what does the theory actually predict we should see here? Our own existence in this specific universe, with its seemingly finely tuned constants, becomes a profound puzzle. Are we a rare statistical fluke in a vast ocean of dead universes, or are we somehow a typical outcome? The answer depends entirely on how we cut the infinite down to a finite, measurable slice. Cosmologists call this choosing a measure. It is a mathematical procedure for sampling from infinity, a way to define a cosmic census. Do we count by volume, by the number of observers, by the time since a universe formed? Each choice leads to wildly different conclusions about what a typical observer should expect to find. One measure might suggest our galactic neighborhood is utterly average, while another could imply we live in an exceptionally privileged and rare bubble. Without a solution to the measure problem, the multiverse hypothesis remains frustratingly vague. It can suggest anything and therefore predicts nothing. Taming this infinite possibility is the crucial next step in our quest to understand the edge of everything, because it forces us to ask not what lies beyond our horizon, but what our own existence tells us about the true nature of the boundless whole. Our very presence here acts as a powerful filter for reality. The Anthropic Principle is the simple, yet profound, idea that any universe we can possibly observe must be compatible with the existence of observers. We are here asking questions about the cosmos, so the universe we find ourselves in cannot be one where life is impossible. This shifts the entire question of why the laws of physics seem so perfectly fine-tuned for life. Think of it like this: if you are dealt a single poker hand, getting a royal flush seems like a miraculous, one-in-a-million event. But if you are dealt trillions of hands, a royal flush is not just possible, it is inevitable. Now apply that to the cosmos. In a vast multiverse, where every possible set of physical constants exists in some bubble, a universe that produces stars, planets, and conscious life is simply one of the hands that was dealt. We are not witnessing a universe designed for us. We are simply the inevitable observers in one of the rare, habitable pockets within an infinite reality. The strength of gravity, the mass of an electron, the force that holds atomic nuclei together, these fundamental constants appear perfectly balanced on a knife's edge. If gravity were slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, galaxies and stars would never have coalesced from the primordial gas. Our existence here is not proof of a grand design, but a powerful example of selection bias. We could not possibly find ourselves in a universe that cannot support us. This reasoning transforms a question of cosmic purpose into one of cosmic statistics. We stop asking why the universe is the way it is, and start asking what kind of universe we should expect to find ourselves in, given that we are here to ask the question. It provides a natural explanation for our universe's apparent perfection, without needing to invoke a creator or an unimaginable coincidence. This perspective profoundly reframes our place in the cosmos. We are not at the center of a universe made for us. We are a fleeting but inevitable product of a vast and mostly inhospitable reality, living on the shores of one rare and precious island in an endless dark sea. String theory offers a breathtakingly concrete, if speculative, vision of the multiverse. It proposes that the fundamental building blocks of reality are not point-like particles, but unimaginably small, vibrating loops of energy. The different vibrational patterns of these strings give rise to all the particles and forces we observe, from electrons to photons. But to make the mathematics of this theory work, these strings must vibrate in a reality that has more than the three spatial dimensions we experience. The theory requires extra dimensions, perhaps 6 or 7 of them, all curled up and compactified on a scale so tiny that they are completely hidden from our perception. Imagine a garden hose seen from a great distance. It appears to be a simple one-dimensional line, but if you could shrink down to an ant's perspective, you would discover the hose has a second dimension, a circular cross-section that loops back on itself. Our entire cosmos could be like that, with every point in our three-dimensional space harboring a hidden, complex, multi-dimensional shape. The specific geometry of these hidden dimensions is absolutely critical. It dictates how the strings within them can vibrate, and since the vibrational patterns determine the laws of physics, the shape of these dimensions effectively writes the rulebook for a universe. A slight change in the compactified geometry would alter the masses of particles, the strengths of forces, and even the number of fundamental forces that exist. This is where the concept of the landscape of vacua emerges. String theory does not predict one unique set of physical laws. Instead, it allows for a staggering number of possible stable configurations for these extra dimensions, perhaps 10 to the power of 500 different ways they can be curled up. Each stable configuration is a vacuum in this landscape, a potential universe with its own unique, self-consistent laws of physics. Our universe, with its specific electron mass and gravitational constant, is just one single, solitary point in this vast, almost infinite cosmic catalog. This provides a powerful physical mechanism for the eternal inflation multiverse. When a new inflationary bubble forms, the process could randomly settle the extra dimensions into one of these countless possible shapes, locking in a new set of physical laws. The edge of our universe in this radical framework might not be a boundary of empty space. It could be a domain wall, a transition zone where the compactified dimensions suddenly shift into a new configuration. Crossing such a frontier would be the most profound journey imaginable. The very rules of reality would change in an instant. Gravity might cease to exist, or light might travel at a different speed. Matter as we know it would likely dissolve, reconfiguring itself according to the new local laws. So the ultimate edge is not a wall of darkness, but a shift in the very architecture of space itself, a doorway to a reality where the fundamental constants are rewritten and a completely new cosmic story begins. Yet this entire cosmic tapestry, from the multiverse to the holographic edge, rests upon a single, staggering event, the moment of creation itself. So what existed before the Big Bang? The most profound answer science can offer is also the most unsettling. There was nothing, but in the quantum realm, nothing is never truly empty. Even in the most perfect vacuum we can conceive, the void is alive with activity. Virtual particles spontaneously flicker into existence, borrowing energy from the void for a fleeting instant before annihilating each other and vanishing back into the stillness. This is not just a theoretical idea, it is a verified phenomenon, a fundamental seething of reality at the smallest scales. From this unstable quantum nothingness, our entire universe could have been born. Theories like the Hartle-Hawking no-boundary proposal offer a vision of spontaneous creation. They suggest the universe appeared from nothing through a process akin to quantum tunneling, the same kind of probabilistic leap that allows an electron to magically appear on the wrong side of an energy barrier. In this genesis, there was no fiery explosion in a pre-existing void. There was no before. The event was the beginning of time itself. Asking what came before the Big Bang becomes as meaningless as asking what is north of the North Pole. The concepts of before and after, of outside and inside, simply did not exist until the universe began. This transforms our understanding of the ultimate edge. The boundary of our cosmos is not a place in space you could ever hope to reach. It is a boundary in time, the very first moment, the origin of space-time. We are not living inside a bubble that has an edge. We are living on the other side of the very beginning of everything. The cosmic horizon we see is just a later consequence, but the true, final frontier is the moment of quantum genesis itself. This provides a scientific, if utterly mind-bending, narrative for the ultimate origin, one that replaces a divine creator with the unpredictable, creative churn of quantum probability. The universe did not come from somewhere else. It came from nowhere, a spontaneous fluctuation in the absolute void, giving rise to all of space, all of time, and all the wonders within it. Our own minds may be the final, impenetrable horizon. We are prisoners of scale, our consciousness forged in a world of medium-sized objects moving at moderate speeds. Our brains evolved to spot predators on the savannah and to throw a spear, not to intuitively grasp a reality where space is relative and particles can be in two places at once. This creates a fundamental disconnect between the universe as it is and the universe as we are able to perceive it. Our most powerful tool, science, is built upon a foundation of empirical observation and mathematical logic. We devise experiments, we collect data, and we construct models that describe the cosmos with breathtaking accuracy. Yet these models are not reality itself. They are maps, and like any map, they have their limits of resolution. When we push our inquiries to the very edge of existence, to the singularity of a black hole or the first moment of the Big Bang, our equations break down into infinities, signaling that our map has reached the end of the page. Asking what happened before the Big Bang may be a question that has no more meaning than asking what sound the color blue makes. Our concepts of before and after, of cause and effect, are products of the space-time that began in that very event. We are trying to use the rules of a game to describe what exists before the game has even started. Our language and our logic are so deeply rooted in the local, causal structure of our universe that applying them beyond its birth is like a fish trying to develop a theory of fire. The fish understands fluid dynamics and pressure, but the concept of combustion in a gaseous atmosphere is utterly outside its frame of reference. We are those fish swimming in the cosmic ocean, trying to comprehend the dry, fiery laws of a meta-reality that operates on a completely different set of principles. This is not a failure of science, but its greatest strength, the humility to recognize its own boundaries. The true edge of everything may not be a place in space or time, but the limit of our own comprehension. Every new discovery pushes that boundary back, yet the ultimate nature of what lies beyond may forever remain just out of reach, a silent, magnificent mystery that our minds are simply not built to hold. This cosmic isolation forces a confrontation with one of philosophy's oldest puzzles. We are presented with a universe that logic tells us is almost certainly far larger than what we can observe, yet we are permanently confined to our own local neighborhood, our causal patch. This situation mirrors a form of cosmic solipsism, a profound loneliness on the grandest scale. We can theorize about the greater whole, but we can only ever truly know and verify the reality contained within our own sphere of light. This leads to a deeply unsettling question about the nature of existence itself. When a distant galaxy is carried by the expansion of space beyond our cosmic horizon, what becomes of it? From our perspective, its light can no longer reach us. No signal, no force, no particle from that galaxy can ever again interact with our own. In any practical, physical sense, it has vanished from our reality. So, does it cease to exist for us? Is reality defined not by what is, but solely by what we can interact with and measure? These are not new questions. They echo ancient philosophical debates between idealism and realism. The idealist might argue that what we cannot perceive might as well not be real, that the universe is, in a sense, a construct of our observation. The realist would counter that the galaxy continues to exist with perfect objectivity, regardless of our inability to see it, that there is a reality independent of any observer. Our cosmic horizon does not solve this debate, but it physicalizes it, carving the philosophical dilemma into the fabric of the cosmos itself. It imposes a fundamental and unbreakable limit on human knowledge, a permanent veil drawn across most of existence. This is a humbling realization, a core part of our cosmic story. We are not just limited by our technology or our intellect, but by the very laws of physics, which decree that some mysteries will remain forever beyond our grasp. The edge of everything is not just a frontier of space, but a boundary for the human mind. This ancient shell of light is more than a fossil, it is a detective's canvas. Cosmologists are forensic scientists of the cosmos, scrutinizing the cosmic microwave background for the slightest flaw, a tiny crack in the standard story that could reveal a world beyond our own. They search for anomalies, strange patterns or asymmetries that the theory of inflation cannot easily explain. One of the most tantalizing of these is the so-called cold spot, a vast, unusually cool region in the CMB that appears too large and too cold to be a simple statistical fluke. One provocative explanation is that this cold spot is a cosmic bruise, the imprint of a collision with another bubble universe in the multiverse. In this speculative scenario, as our inflationary bubble expanded, it may have gently bumped into a neighboring reality. The energy released at that primordial boundary could have left a faint, cooler scar on our sky, a permanent mark of a reality we can never directly visit. This idea is, of course, highly controversial. Most scientists argue that the cold spot is likely a rare but natural fluctuation, a cosmic roll of the dice that just happened to turn up snake eyes. Yet the very fact that such an extraordinary explanation can be seriously proposed shows how far we are willing to stretch our instruments and our minds. We are using the oldest light in existence as a probe, searching for reflections from outside our cosmic cave. A single, confirmed anomaly in this primordial glow would be revolutionary. It would be the first empirical clue, a message in a bottle from the shores of another universe, telling us that our reality is just one island in an infinite archipelago. The hunt for these clues has become one of the most intense pursuits in modern cosmology. Space-based telescopes and ground-based observatories are mapping the CMB with ever-increasing precision, their electronic eyes scanning for any other imperfection, any subtle whisper in the noise that might betray the presence of the greater whole. We are sifting through the ashes of creation, hoping to find a fingerprint that does not belong to our universe alone. These cosmic gateways have long captured our imagination. Science fiction paints black holes as tunnels to other dimensions, a thrilling shortcut across the cosmos. The mathematics of Einstein's general relativity does offer a tantalizing possibility, the Einstein-Rosen bridge, more popularly known as a wormhole. Picture the universe as a vast, flat sheet of paper. If you wanted to travel from one edge to the other, it would be a long journey. But what if you could fold the paper, bringing those two distant points together and poking a hole through the gap? That is the essence of a wormhole, a theoretical shortcut through the fabric of space-time. It could connect two wildly separate regions of our own universe, or, in some speculative solutions, serve as a bridge to an entirely different cosmic realm altogether. But this is where the dream collides with harsh physical reality. For such a passage to be stable and traversable, for it not to collapse into a pinprick the instant something tries to enter, you would need a bizarre and hypothetical substance to prop it open. This is exotic matter, a theoretical material that possesses negative energy density, effectively pushing the walls of the wormhole apart against the crushing force of gravity. We have no evidence such matter exists or can even be created in sufficient quantities. Without it, any wormhole would be catastrophically unstable. The journey through would be unimaginably brief, ending not in another universe but in a violent collapse. And then there is the final barrier, the singularity itself. At the very heart of a black hole, according to our current models, lies a point where density and gravity become infinite. Here, the very laws of physics as we know them cease to function. Space and time as coherent concepts simply end. This is not a spatial edge you could touch or see, but an edge of predictability, a boundary beyond which science cannot currently peer. So while black holes are almost certainly not the convenient stargates of fiction, they are something perhaps even more profound. They are natural laboratories where space and time are warped to their absolute limits, offering us a front-row seat to the most extreme physics in the universe. They force us to ask what truly happens when the rules break down, presenting an edge not of location, but of understanding itself. This paradox strikes at the heart of physics itself. The event horizon of a black hole presents a fundamental conflict between our two most successful theories. On one hand, quantum mechanics insists that information is sacred, never truly destroyed. The details of the book you just burned may be scattered and chaotic, but in principle, they are still encoded in the smoke and ashes. On the other hand, Einstein's general relativity paints the event horizon as a one-way street. Anything that crosses it, whether a book, a planet, or a person, is simply gone. Its information forever trapped and inaccessible to the outside universe. This is the black hole information paradox, a deep crack in our understanding of reality. To resolve it, physicists have proposed a startling idea, the firewall. Imagine approaching what you believe is a smooth, empty space, the event horizon. Instead of floating through unnoticed, you instantly collide with a blazing wall of high-energy radiation, a cosmic shredder that incinerates you and every bit of information you carry into pure energy. This violent solution saves the principle of information conservation, but at a terrible cost. It shatters a cornerstone of general relativity, the equivalence principle, which states that an observer falling freely should feel no special effects when crossing the horizon. There should be no dramatic fire, no wall, no sign that you have passed the point of no return. You would notice nothing strange until the tidal forces of the singularity eventually pulled you apart. So we are left with a seemingly impossible choice. Either information is lost, undermining the foundation of quantum theory, or the event horizon is a place of unimaginable violence, contradicting Einstein's elegant theory of gravity. This is not just an academic debate about black holes. The very nature of our cosmic horizon is at stake. That distant boundary, the limit of our observable universe, is also a kind of event horizon, a surface from which we can receive information but never send it back out. If a firewall can exist at the edge of a black hole, could a similar barrier of searing energy exist at the edge of our entire cosmos? a final, impassable wall for any information trying to reach us from the great beyond. The edge of a black hole is more than a cosmic curiosity. It is a laboratory for the most extreme physics, a place where our theories are pushed to their breaking point, forcing us to invent a new language that can finally unite the very large with the very small. Our reality may be nothing more than an incredibly advanced simulation. This is the simulation hypothesis, a modern philosophical argument that suggests the cosmos we perceive is not the base level of existence, but a complex digital construct, a universe running on some unimaginable computer. In this view, the fundamental laws of physics are not discovered but programmed, the unwavering rules of the code. The edge of our observable universe would then not be a physical or temporal boundary at all, but a computational limit. It would be the point where the simulation's rendering engine stops, where the allocated memory for our particular cosmic instance is exhausted. The holographic principle, which suggests all the information in our three-dimensional reality is encoded on a two-dimensional surface, fits eerily well with this idea. A simulation would not need to calculate every single particle in full detail at all times. It would only need to store and process the information required to create a consistent experience for the observers within it. Much like a video game only renders the parts of the world the player can currently see. This could explain some of the deepest puzzles in quantum mechanics. The strange phenomenon where particles seem to lack definite properties until they are measured could be a clever programming optimization, a way for the system to save processing power by not calculating the precise state of something until it is absolutely necessary. The very finiteness of the speed of light, the ultimate speed limit of our universe, could be the processor clock rate, the maximum speed at which information can be updated across the simulation. What we perceive as the smooth fabric of space-time might be a pixelated grid on a scale so infinitesimally small that we cannot detect it. If this is true, then the ultimate boundary of everything is not a wall of darkness or a shift in physical laws, but a buffer overflow in a cosmic computer. Our search for the edge becomes a search for glitches in the matrix, for tiny errors or inconsistencies in the laws of nature that might reveal the underlying code. While this idea remains firmly in the realm of speculation, utterly untestable with our current science, it forces a profound shift in perspective. It asks us to consider that the final frontier may not be made of space or time, but of bits and processing cycles, a digital horizon drawn by an intelligence we can never hope to comprehend. These cosmic truths do not remain in the abstract. They reach down and touch the human spirit, reshaping our sense of self and our place in the grand scheme. Staring into the cosmic abyss can trigger a profound psychological shift, a dizzying mix of awe and humility known as the overview effect. Astronauts who have seen Earth from orbit often report this transformative experience, a visceral understanding that all borders are human inventions and that our planet is a solitary, fragile life raft in a vast, empty sea. This cosmic perspective can dissolve tribal conflicts and ignite a powerful drive for global unity and environmental stewardship. If this is our only home in the immensity of space, then its preservation becomes our most sacred, shared responsibility. Yet the same vista can also cast a long, cold shadow. The sheer scale of an infinite, uncaring cosmos can induce a deep existential dread, a feeling that our struggles, our art, and our very lives are utterly insignificant in the face of such boundless indifference. If we are just temporary patterns of stardust on a random rock, adrift in a multiverse of dead realities, then what is the point of it all? This tension between awe and anxiety is a deeply human challenge. It forces us to confront a fundamental choice. Do we see our smallness as a reason for despair or as a liberation? In a universe without a prescribed purpose, we are free to create our own meaning, to find value in connection, in discovery, and in the brief, brilliant flash of consciousness we are granted. The journey to the edge of everything, therefore, is not merely a quest for external knowledge. It is the ultimate mirror, reflecting back at us the question of what it means to be human in a cosmos that is silent to our hopes and fears. How we answer that question individually and as a species may be the most important discovery of all. Our technological eyes on the cosmos are about to receive a monumental upgrade. While the James Webb Space Telescope has already revolutionized our view of the infant universe by capturing the faint infrared glow of the first galaxies, this is merely the opening act. A new generation of observatories designed to perceive the universe in entirely different ways is on the horizon. These are not just bigger telescopes, they are entirely new senses for humanity. The Laser Interferometer Space Antenna, or LISA, will not look for light at all. It will listen. This fleet of 3 spacecraft, flying in a precise triangular formation millions of kilometers apart, will detect the ripples in spacetime from cataclysmic events we cannot see, like the merging of supermassive black holes. But its most profound target is the faint, primordial hum from the universe's first instant, the gravitational wave background from inflation. Hearing that echo would be like unlocking a recording of the Big Bang itself. At the same time, the Nancy Grace Roman Space Telescope will conduct vast cosmic surveys, mapping the distribution of dark matter and the history of cosmic expansion with a field of view 100 times larger than Hubble's. It will peer into the nature of dark energy, measuring its influence over time to see if it is truly constant or something far more dynamic and strange. And on the ground, next-generation experiments for the cosmic microwave background, often called CMB Stage 4, will map the remnant heat from the Big Bang with such exquisite detail that they could detect the faint imprint of gravitational waves on that ancient light, or even spot the subtle distortions that might hint at a collision with another universe. Each of these missions delivers a unique piece of the puzzle. One listens for the vibrations of creation, another maps the invisible scaffold of reality, and the third examines the foundational blueprint in ultimate detail. Together, their data will either solidify our current models of the cosmos or, far more likely, shatter them entirely. The edge of everything is not a static frontier. It is a horizon that recedes as our tools improve. And with these new instruments, we are not just building better telescopes, we are forging the keys that might finally unlock the door to what lies beyond. Our ancestors gazed at the same stars and told stories of cosmic oceans and world turtles. Today, we chart cosmic inflation and multiverses. This is not a break from our past, but its direct continuation. The great mythological boundaries of old, like the edge of a flat world or the celestial spheres that held up the heavens, were humanity's first attempts to map the limits of existence. They were stories that gave order to a chaotic and unknown cosmos, answering a deep, psychological need to define our environment and our place within it. The observable universe, with its particle horizon set nearly 14 billion light-years away, is our modern version of the Pillars of Hercules. It is the ultimate "here be dragons" on our scientific maps, a boundary beyond which we can only speculate. The tools have evolved from oral tradition to quantum physics, from shamans to supercomputers, but the fundamental human questions remain hauntingly similar. Where did everything come from? What lies in the great unknown? And are we a central part of this story, or a mere footnote in an infinite text, seeing science as the latest chapter in this ancient, ongoing narrative transforms it? It is no longer a cold, detached collection of facts, but a deeply human endeavor, a collective search for meaning written in the language of mathematics. Our quest for the edge of everything is, and has always been, a quest to understand ourselves. Perhaps our universe is not a one-time event, but a single heartbeat in an eternal cosmic rhythm. The idea of a cyclic universe challenges the very notion of a definitive beginning and end, proposing instead an endless series of cosmic cycles. In this grand vision, the universe expands from a hot, dense state, evolves as ours has, and then, instead of fading into eternal cold or tearing itself apart, it reverses course. All matter and energy are pulled back together in a monumental big crunch, collapsing back into a singular, ultra-hot state, only to rebound in another big bang, starting the entire process over again. The edge of one cosmic epoch is not a wall of darkness but a temporal turning point, the moment of collapse that gives birth to the next cycle. What we perceive as our ultimate origin in the Big Bang might have been merely the latest rebirth in an infinite chain. This transforms the haunting question of what lies beyond the edge into a question of what came before our cycle, pushing the mystery of origins back into an immeasurable past. One particularly compelling version of this idea is the ekpyrotic model. It envisions our four-dimensional universe as a three-dimensional membrane or brain floating within a higher dimensional space. In this silent, unseen realm, another brain might exist parallel to our own. Our entire cosmic history, from the Big Bang to the present day, could have been triggered by a gentle collision between these two worlds. That moment of contact released an immense amount of energy, flooding our brain and setting off the expansion and evolution we observe today. The universe did not erupt from a single point, but was ignited across a vast area by this encounter in the bulk. This model suggests a cosmos without a true beginning, where brains move, collide, and separate in an endless, graceful dance across higher dimensions. Each collision is a new Big Bang, a new universe born from the ashes of the previous encounter. If this is true, then the cosmos is eternally renewing itself. Each cycle might even carry faint echoes from the one before it, like a cosmic genetic code. The patterns in the cosmic microwave background, the very large-scale structure of galaxies, could hold subtle imprints, scars from a previous incarnation of reality. We might be living in a universe with a rich ancestral history, whose stories are written in the fundamental constants and the geometry of space itself. This cyclic view offers a profound alternative to a singular creation, presenting a cosmos that is both ancient and forever young, where every ending is merely a prelude to a new beginning. Time itself begins to fray at the cosmic boundary. Our comfortable, linear experience of past, present, and future, that steady tick of a clock, is a local phenomenon, a rule that may not apply everywhere. As we approach the theoretical edge of our universe or rewind the clock to the Big Bang, time behaves in ways that defy all intuition. At the moment of creation, the density and temperature were so immense that the very fabric of space-time was woven together. At that singularity, the concept of a before becomes as meaningless as asking what is north of the North Pole. There was no time for anything to come before. The universe did not appear in time, it appeared with time. This is the ultimate temporal edge, a boundary not just of space, but of causality itself. In the frothing sea of the multiverse, this strangeness only deepens. If other bubble universes exist, each may have been born with its own unique arrow of time. In one universe, time might flow at a radically different rate, where a second for us is an eon there. In another, the arrow of time could be reversed, with beings who perceive our future as their past and our birth as their end. The very direction of time, the reason we remember yesterday but not tomorrow, is intimately tied to the increase of entropy, the universe's relentless slide from order to disorder. Yet why the early universe was in such an ordered, low entropy state to begin with remains one of physics' greatest unsolved mysteries. If we could somehow stand at the spatial edge of our cosmic horizon, we might find that time is not a constant river but a tangled delta, slowing to a crawl or perhaps ceasing to have any meaning at all. The edge of space and the beginning of time are not separate mysteries. They are a single, profound enigma, two different expressions of the same fundamental limit to our reality. The universe is not a uniform sea of stars, but a vast and intricate cosmic web. When astronomers map the distribution of galaxies, they reveal a structure of breathtaking scale, with brilliant filaments and dense clusters of galaxies separated by unimaginably large, dark, and nearly empty regions known as cosmic voids. These are not the edges of the cosmos, but rather immense deserts of space within it, some spanning hundreds of millions of light years. They are the dominant feature of our universe, the empty spaces in the grand cosmic tapestry. The formation of this web is a story written by gravity and shadow. In the early universe, light over densities, those primordial quantum ripples magnified by inflation, began to pull in dark matter and gas. Over billions of years, gravity sculpted these regions into the dense walls and clusters of the web. Meanwhile, the underdense regions were left behind, expanding faster than the universe itself as matter flowed out toward the denser filaments. These voids grew, becoming ever more empty, their internal space stretching into profound darkness. This evolution makes them perfect natural laboratories for studying dark energy. The accelerated expansion of the universe is most evident in these empty places, where the repulsive push of dark energy meets the least resistance from gravity's pull. By measuring how voids grow and change over cosmic time, scientists can probe the strength and nature of this mysterious force. Consider the Boötes void, one of the largest known. This spherical near-emptiness is about 330 million light-years across. To grasp its scale, imagine placing our Milky Way galaxy at its center. From that vantage point, the nearest major galaxies would be so distant and faint that they would have remained undetectable to our telescopes until well into the 1960s. We would have lived for most of human history in a sky with almost no nearby galaxies, believing our own island of stars to be a lonely exception in a largely empty cosmos. These voids are not completely barren. A handful of isolated galaxies do cling to existence within them, like lone homesteads in an immense desert. Yet their overwhelming emptiness is a powerful reminder. The cosmos is defined as much by its absences as by its presences, and the true architecture of reality is written in these sprawling frontiers of nothingness. This profound silence from the cosmos presents a haunting question. If the universe is so immeasurably vast and ancient, with countless worlds that could harbor life, why do we hear nothing but an endless, empty static? This is the core of the Fermi Paradox, a puzzle that grows only deeper the more we learn about cosmic horizons. We now understand that the universe is not just filled with stars, but potentially with life, yet we are surrounded by a profound and unbroken quiet. One of the most compelling solutions to this paradox is written in the very nature of the cosmic horizon itself. Advanced civilizations could be flourishing in galaxies, now racing away from us faster than the speed of light. Their signals, no matter how powerful, are chasing a horizon that is receding even faster. We are like two ships on a dark, expanding ocean, each sailing away from the other so quickly that the light from one vessel's lantern can never reach the other. Even if a message were sent, the space between us is stretching so rapidly that those signals would be stretched into undetectable whispers, their energy dissipated across an ever-widening gulf. The universe's accelerating expansion, driven by dark energy, is actively building higher and thicker walls between islands of life. It is not that the cosmos is empty, but that we are being physically isolated from its other inhabitants, locked inside our own celestial prison. This isolation becomes even more absolute within the framework of the multiverse. Intelligent life could be thriving in a bubble universe right next to our own, separated not by distance, but by the fundamental laws of physics. We are like neighbors living in adjacent apartments, but with a wall between us that is not just brick and mortar, but a barrier between different dimensions of reality. No signal, no probe, no form of energy we can conceive of could ever cross that divide. The cosmic horizon, therefore, imposes a double loneliness. It first limits what we can see, and then it dictates who we could ever hope to meet. We may be living in a cosmos that is truly, vibrantly alive, a grand galactic community, yet we are permanently confined to our own solitary room, listening for a knock on a door that does not exist, in a hallway we can never enter. Our journey to the edge of reality reveals that the greatest frontier is not a place, but a question. We have traveled from the tangible limit of our observable universe, a sphere defined by the finite speed of light, to the dizzying possibilities of a multiverse and the illusion of a holographic projection. We have witnessed how dark energy actively forges our cosmic prison, pulling a curtain of permanent darkness across the cosmos, and how the faint echo of the cosmic microwave background serves as both a baby picture and a profound boundary. The tools of science allow us to peer into this abyss, to infer from the subtle patterns of quantum fluctuations and the relentless push of expansion what the ultimate nature of reality might be. We construct models of cyclic universes and cosmic landscapes, not because we can visit them, but because the human drive to understand is as relentless as the expansion of space itself. This quest to comprehend the edge is woven into our very spirit, a fundamental urge to push against the boundaries of the known. The physicist John Archibald Wheeler once beautifully captured our situation, noting that we live on an island of knowledge surrounded by a sea of ignorance. As our island grows, so too does the shoreline of that vast, unknown ocean. Let this understanding inspire not a sense of dread, but of profound wonder and an unquenchable curiosity. The universe is far stranger and more magnificent than we ever dreamed, and the search itself gives our brief moment of consciousness meaning. What do you believe lies in the infinite dark beyond our sight? Share your thoughts in the comments and join us as we continue our voyage to the furthest frontiers